Today we're very happy to have Affiliation to University of Florida talk about the mathematical legacy of Hel Braun.
Great, thanks. I'd like to thank Wei and Camillo for inviting me to speak. And I'd also like to thank the IAS for hosting me this year. It's been really, really great being here. So today I want to tell you about some of the math of someone named Hel Braun. And if you're not familiar with Hel Braun, that's not at all surprising. Before I get going, I just want to tell you briefly how I first came upon Hel Braun. So a few years ago, I was preparing my lectures for the Arizona Winter School, which, in case you don't know, is a major workshop for grad students in arithmetic, geometry, and number theory. And in 2022, the topic was modular forms beyond GL2. And so each of the 4 lecturers, I was one of them, we had a particular group that we were looking at. And I was going to lecture on modular forms on unitary groups. And as I was preparing my lectures and manuscript, I thought, I wanted to just get a sense of the history. Like, when did these really start to become important for context? And I already had a story in my head, which was, well, it must go something like this. You can look at modular forms in different kinds of groups. Some groups are more interesting than other kinds of groups, and some groups are more amenable they have structures that are more amenable to study than other kinds of groups. Unitary groups, particularly in the context of the Langlands program, turn out to be a particularly useful class of groups due to their associated structures. And so I'm expecting that I'm going to start to find this percolating in the literature in the late 60s, early 70s in the context of the Langlands program. And as I do my search, I narrow down to a special case called Hermitian modular forms. And my story was completely wrong. So much earlier, it turns out, I stumble upon these papers that are much earlier in the Annals of Math. There was a series of 3 papers, Hermitian modular forms 1, Hermitian modular forms 2, Hermitian modular forms 3 in 1949, 1950, and 1951, in which someone definitively defines this as a Hermitian modular form and starts to develop the theory. And that person's name was Hel Braun. And this was kind of strange to me because I don't think I had ever heard, at least I was never conscious of having heard of Hel Braun. And this is an object, like, I'm supposed to be an expert in this topic. I'd been studying it since my dissertation. If I had to list the key figures, Hel Braun's name would not be among them. And so eventually feeling somewhat embarrassed, I reach out to a few senior members of my field who also have an interest and expertise in history, and they confirm, yes, that's right. This is when Hermitian modular forms are first defined. But I couldn't, I was hitting dead ends as I tried to get more information. I'm like, that's not that surprising. Hel Braun's a woman mathematician, late 40s, early 50s. There's probably just not that much there to see. And I am careful to cite her, tell my students to cite her, but kind of go my way, not expecting that there's that much. I did find out she was the 2nd woman after Emmy Noether to habilitate in math at Göttingen, and then for over 50 years after that, there wasn't another woman to do that. But she's obviously much less well-known than Emmy Noether. Like, if I had said mathematical legacy of Emmy Noether, you'd all have something in your head. And so I get on with life, and I fast forward several years. It's fall 2024. I'm here at IIS in Fold Hall, and Akshay Venkatesh, I just learned, was interested in math history. So I say, have you heard of Hel Braun? And he says, oh yeah, we have archives for her here. And it's like, no. And so he introduces me the next day to Caitlin Rizzo, and next thing I know, I'm in the archives here. Caitlin Rizzo is the archivist, and she brings out these folders. Hel Braun was a member at IAS in 1947 to 48, and as I learned later, the first of those 2 papers about Hermitian modular forms were work that she did here. So now my interest is piqued. I found out there's much more to Hel Braun. The files here are mostly focused on non-mathematical issues like immigration, but I'm like, wait, there's more going on, and so I end up going up to the archives at NYU because there's correspondence between her and Courant, and then I order a ton of digitized files from Göttingen. I have about 200 files, 200 pages from there, which I'm still going through. And the story just keeps shifting as I go along. both mathematically and in terms of broader factors. So why does this matter mathematically? First of all, her math is, some of her math at least, is still relevant, still interesting today. But the context around it's often been stripped of its context, and because of that, some things have just fallen by the wayside that are interesting and useful. We don't even know to go look for. But even for things we do know, like not having that context is a real disservice, because like I think most of us don't understand math as like an isolated definition here and an isolated theorem there, but you want connections between things to get a robust understanding. And if we don't kind of set things up in that way and people don't know where to look or know how things are connected, we're doing a real disservice to future generations of mathematicians. So in this talk, my goal is basically to introduce some of Braun's math, plus context surrounding its development. And her math actually, it turns out, comes in 3 phases. What I looked at was kind of the middle phase, was what I had stumbled upon. So there's these 3 phases. I'll get to 3 in a moment. So this is maybe what you might think of as kind of these okay. Classical number theory topics. The next is modular forms and automorphic forms. And then it looks like there's a jump discontinuity if you just look at the publicly available math that you can easily access. But there's actually, I'm going to put 3 in 2 pieces. So there's a parenthetical remark, which is stuff I learned from looking at her correspondence with the mathematician Hans Maas. And then there's the part you can actually find in publications. So the last part of her career, which is quite substantial, is algebra, in particular primarily focused on something called Jordan algebras. But what leads her there actually is geometry. Without looking at these letters, I figured there's just some jump discontinuity, and as I'll get to later in the talk, there would be good reason for her just to run away from here and do something different. But in fact, there's a very logical continuum which leads her through here to land on algebra. It's not as so, I'll get to that near the end. So I just want to start now with phase 1, which is where her thesis and habilitation were. And I'm going to start with a very old question. So but way before Braun, way before any of us. So how many ways, or even just an existence statement, can you, so if you're given, say, a positive or non-negative integer n, how many ways can you write n as a sum of k squared? So this goes back to the ancient Greeks. So, and then was investigated more thoroughly later. So I'm just going to introduce some notation I'll use. So we're just looking at k tuples of integers, a positive, negative, or 0, such that sum of their squares gives us our specified number. And so just for example here, if I look at the number 7, I'm going to get 0 for it. So there exists none for the first 2, but at least in some sense, Diophantus seemed to assume that there were 4 squares. In what sense he knew that isn't clear, but in the 1770s, or in 1770, Lagrange shows that you can always write an integer as a sum of 4 squares. So a second question, there's a generalization of this, is you could instead say, suppose you're given a positive definite quadratic form with integer coefficients, and suppose your quadratic form is in n variables, you can ask an existence or quantification answer about writing this as a sum of squares. So how many ways can you, let's just call our form Q. Right, Q as a sum of, say, k squares of linear terms. So to be clear, this is a direct generalization. If n equals 1, then we are back in this case. So if Q, say, is n times x squared, this is my one variable here, then we're just asking about Rk of n. So this also gets an existence statement in the 30s due to Mordell and co, at least as long as you have no more than 8 squares. And then in her dissertation, Hel Braun gives a formula for this. So shall So Hel Braun was a student of Carl Siegel, who later became a permanent member here. But at the time, she wrote her dissertation at Frankfurt under his direction. And so in her thesis, which she defended in 37 and was published in 1938 in Krella, she gives a formula for, let me just, I guess I didn't give this name, I think it's clear what I meant. No one stopped me. This, how many ways I'm calling, just an analog with what we just had. Rk of Q. For 1 between n and 8. So this builds in a similar way to how various people, in particular Gauss and Jacobi and Eisenstein, gave formulas here. She gives a formula, and this formula here, I'm not right, I hope to write it down, but anyway I could write it that was appropriate for a colloquium. By the time I simplified it enough, it was back at specialized to just restating a formula that's already due to other people. So I'm just gonna say that it's specialized, it recovers as a special case. The formulas of Gauss, who handled 2 and 3 squares, and Jacobi, who's going to come up again later, for also 2, 4, 6, and 8 squares, and Eisenstein, who handled 5 and 7 squares.
Is that n between 1 and 8 or k between 1 and 8?
What?
Is it n between 1 and 8 or k between 1 and 8?
Oh, I do want K, thank you. Yes, I do want K. Thank you. These formulas here were for Rk of n. So just for example, for one that I think is kind of the most form, like if you're not in number theory, I think, or even if you are, the one we most often see is the 4 squares result of Jacobi. So in 1834, in the mid 1830s, he's investigating these guys and shows that this is 8 times the sum of the divisors d of n that are not divisible by 4. So she recovers all of these as a special case of her elaborate closed form formulas. And this thesis gets really good praise. Siegel writes that in the write-up that her work's going to be of interest not just to number theorists, but to all mathematicians, and that we have a lot to look forward to with her innovations. He's a big supporter of her. Early on, she was considered the top student that year. She goes on to do some more in this direction, but first I just want to mention a generalization, which is going to lead up to her habilitation work. So generalization. So now let's have two quadratic forms, and Siegel is the one. The thing I'm going to tell you right now. First, Siegel starts to study a lot, which is, so now let's take, we still have our Q from before, and we'll have another guy, T, which are still positive, definite, quadratic forms with integer coefficients, and I'm just going to identify them with the associated half integral symmetric matrices by the usual operation going between quadratic forms. And matrices, half integral means on the diagonal, you have integers. Off the diagonal, you have half integers. So the bilinear form there, when you ask what quadratic form you get one with integer coefficients. And I'm going to assume that this guy is in, this is going to be in n variables. This is in, say, m variables. And we can just jazz up this thing we're looking at slightly, this R. Now we're going to look at our Q of T and ask about, what's the number? Oh, I didn't write number here. So it's hopefully clear from context that I'm talking about a number. I want the number of matrices that are m by n with integers in Z that take me from one of these quadratic forms to other. So I want to ask if they're equivalent over Z. And so I want to know, can I get from, they do a transformation that gets me from Q to T, and I want to know how many ways can I do this. So Siegel studied this a lot. Just to be clear, we haven't gone very far at all. If n is 1 here, then we're just asked if n is 1 and Q is, and say m equals k, and Q is the k by k identity matrix, then this is the same thing that we started off with at the beginning. We're back at our k matrix n, say that's our integer, 1 by 1. Then we're back at looking at Rk of n. So we've really just taken a generalization. So Siegel investigates these guys very thoroughly. So they're going to come up again when we get to modular forms. So he investigates this thoroughly. Hel Braun in her habilitation thesis, which she finishes in 41, extends this to the Hermitian setting. So she extends everything Siegel's done. Things get much more complicated, especially if, so let me just, before I get to it and get more complicated, so what do I mean by extend to a Hermitian setting? i.e., replace the integers by the ring of integers in a quadratic imaginary extension of Q. So for example, You could take O to be the Gaussian integers, but you could also take it to be infinitely many other things. And we're going to replace Q and T. These were symmetric matrices. Now they're getting replaced by Hermitian matrices. So their conjugate they're equal to their conjugate transpose. So she develops this theory. She proves all the things that Siegel's initially doing. For these guys, she does here. If the class number is not 1, it gets more complicated. She also proves some things that seem to have no analog in Siegel's setting. But the fact that she's working in this Hermitian setting is going to turn out to be really important for her work to come. So the expertise she's developing here is particularly important. And you might be wondering, like, there's some years here which might make you wonder. Like, she enters university in 33. She's defending her thesis in 37. This is like the Nazis have been really infiltrating like politics is a huge thing taking over universities at this time. So she actually had to leave. She was boycotting a lecture got in some trouble because of politics, so has to go to she was at Frankfurt, has to go to Marburg for a while, eventually comes back to Frankfurt. You might be wondering, how on earth does she say she has habilitates that's not really in keeping with the culture at that time? And what she writes in some writings she wrote about her life is that eventually men are leaving the university, they need more women to do men's work, and she's allowed to habilitate. So that's the circumstances around which this happens. Hasse leaves and she becomes the algebra lecturer. The librarian leaves, she has to manage the library. She's doing all these different jobs, and things are getting to be increasingly a mess in Germany. So Courant, it turns out, had wanted to bring her here actually since before Pearl Harbor, which happened in 41. That didn't work. He was interested in her math. That didn't work out. But she's this rising star. That did not work out. Now the war happens. So now the war ends in 45. And so he resumes trying to bring her over. And this is where this second phase kind of takes off, modular forms. She'd already been starting on this before coming here, but it's going to become a big part of things. So I'll come back to the history in a moment. I just want to start off by telling you a little bit about modular forms. And I'm not going to start, if you're not in number theory, then the kind I'm going to tell you about is maybe not that familiar, but we'll specialize to what you might have seen before. So a Siegel modular form, Siegel did not call them this, he called them modular forms of the nth degree, but eventually they got named after him, is a holomorphic function from what is now called the Siegel upper half space to C. So this is the set of all x plus iy inside of sim n r tensor C over R. This is the same thing as symmetric matrices over C. I'm writing it this way because it's going to be useful for showing parallels later. So it's not just some clunky notation. This means y positive definite. A Siegel modular form, oops, there's an important thing here, of weight k is a holomorphic function on this space such that f of, it's invariant under a certain transformation. So for this transformation property, which looks like this, for all matrices A, B, C, D inside of the symplectic group of degree n with integer entries. So this is the set of all G in SL 2n of Z such that G eta n, let's transpose G equals eta n, where this eta n here is going to show up again. So I want to introduce notation first. I don't have to keep writing this matrix out. It's just -1n, the negative, the identity matrix here, identity matrix here. So this defines some alternating pairing, and we're just taking matrices that are preserving this pairing. And so we've got these guys. Sometimes these get jazzed up over time. So if you want, you can stick this inside of some appropriate subgroup inside of here initially. And for this talk, I'm going to mostly just not specify these guys. And when n equals 1, also need to impose a condition that f is bounded as y goes to infinity. So this condition was actually imposed generally when these were first defined in the 30s. And then in the early 50s, Max Kocher, who it turns, for those of you in number theory, is Kocher of the Kocher principle, so it's Americanized to Kocher principle. Kocher was effectively her student, although if you look at Math Scinet, it doesn't say that. But if you read things, Hassler refers to her as him as her student. And if you look at letters she writing to Moss, she's clearly operating in an advisorial sort of capacity, an important mentor to him. So eventually this boundedness, originally things looked more complicated, but this is how things look today. And in fact, today, various things here get replaced and generalized. But for this talk, we're just going to be at this. So for example, n equals 1 is the usual modular forms you would see in any first course in modular forms. And for this 4 squares theorem, this result here, I said 1834, this is from Jacobi. Jacobi's idea for computing Rk of n for small n invokes modular forms. So his idea is take the function theta of q, q to the n squared, summing over all integers of n. Here q equals e to 2 pi I z. So now if I take kth powers of this function, I end up with a function whose coefficients are precisely the numbers Rk of n, q to the n. Of course, for this to be useful, you have to be able to relate this thing to something where you do know the coefficients. And that's where modular forms come in. So what Jacobi does is he says, well, theta is a modular form. Oh, theta to the k is a modular form of weight k over 2 for not for all of SL2Z, but for some appropriate group we don't need for this talk inside of there. And for weights of low dimension, the spaces he's looking at are very small. So for example, theta squared lies in a one-dimensional space. So if he knows a generator and knows how to get the Fourier coefficients for that guy, he wins. Yeah.
There are 2 different ends there, right?
So I have too many ends.
Yeah.
Oh, wait. Oh, okay. This is just an indexing. Oh, I see. Oh, you're right. Yes. Okay.
And was the integer we're trying to decompose.
Yes, it is. But we have an n. You're worried about this n and that n?
Yeah.
Yeah. Let me just call. Okay. Hold on. We'll keep this here, and we'll call this guy capital N, and At some point, you might have to adjust though and go from context, so even this is gonna correspond to the capital N I used before. So as long as I keep this capital N, there'll be no ambiguity. So, but you might have to catch me at some point because I do use both, and I call both little n for myself. So I think I've fixed, and again, for people who didn't catch this, this is going to agree with what I called capital N before. And the reason I had that capital N was because I realized I had a thing earlier in my mistake where I had two little n's. So just stop me if I do that again. So when this is theta to the 4, so it's weight 2, the particular space of modular forms thing is 2-dimensional. So he has a little more work to do, but if he understands those forms, he's in business. And in fact, so he can express theta k for these small values of k in terms of particular modular forms whose Fourier coefficients we can express explicitly. We know formulas for, not just like, well, we'll call it RK of n, but we know formulas for them. And namely, these guys are something called Eisenstein series. So you see these guys in a first, if you take a first course in modular forms, they look like 1 over mz plus n to the k, where m and n are running over some lattice. The first ones you usually see look like this, and then you can cook up this plus variants of this. There's various variants which do come into play in Jacobi's work, and you have to be careful, of course, about convergence. So, for example, this guy, well, it's the way I've written it, 0 if k is 3, but to converge absolutely, you need k at least 3. So the interesting ones start at k equals 4, but we sometimes have ways of doing analytic continuation. So those small k's, k equals 1, k equals 2, we're still able to Jacobi is still able to bootstrap and get around. So convergence is a real issue, and how to make sense of things in because low weights are where he's able to work here, but there is some work to do there, but not what we're gonna focus on in this talk. But an issue of convergence is gonna come back later, so I just wanted to mention that. So people looks at theta q of z, for z here is now in H capital N, the set of all RQ of t, q to the t, where q is equal to e to the 2 pi I trace p z, and t here is running over certain half integral positive definite symmetric matrices. So this is an analog from our generalization of what we had for those theta functions of Jacobi. And he does lots of things with these. In particular, this is modular in the sense of Siegel modular forms of weight m over 2, where these are the same. So n went with our, do I have my things? Did I have these backwards? Shoot. It was n variables and no, okay. So this is of weight m over 2, and he takes this much further. He relates basically this is a whole field someone could give many talks about, but weighted averages of some of these guys theta 2 to certain Eisenstein series relating these guys, which eventually leads to work of Siegel-Vey, which in some sense inspires the ongoing work in the Kudla program. So it's like some whole direction of things one could discuss. What I want to get back to is Hel Braun's work. And before I get to these so-called Hermitian modular forms, I want to note that I just told you like a minute ago, convergence is really important. Siegel actually kind of gave a weak convergence result. His convergence the information he gave was like, he gave a not sharp bound for when you get convergence, which was quadratic in n, but Braun shows that these Siegel's Eisenstein series, which are some generalization of what's over there, the appropriate generalization, converge absolutely for weight greater than n plus 1. Siegel had a bound that involved an n squared term plus other stuff, and he gives her lots of credit. In his papers, he's saying that she's been a really important figure here. So now she's been involved in the Siegel modular forms, also on her own back in Germany, had been looking at Hermitian forms. And so she now puts this together into Hermitian modular forms. So these guys, the idea is similar to Siegel modular forms, except replace Hn here by the Hermitian upper half space, which is now going to be the guys inside of Hermitian matrices n by n, tensored over R with C, still positive definite. And we're also going to replace the symplectic group by the unitary group of signature N. She also has to do this each time. She has to fix her ring of integers O in a quadratic imaginary extension. So the same sort of setup that she was in back in her habilitation. So UNN here is now the set of guys inside of 2n O, such that G bar transpose A to N G equals A to N, which corresponds to preserving a certain Hermitian pairing of signature and N. So this is the thing she defines and begins to develop while she's at IIS in 47 to 48 that ends up in those 3 papers in the Annals in 1947, 1949, 1950, 1951. So, and defined and developed by Braun, starting in the Annals in 49, 50, and 51. So one thing I learned looking at her archives here when I first went to them was that Siegel was in love with Hel Braun. He refers to her as his one true love, his fiancée. This then, of course, gets, I mean, this is, you see this in the files, I took it at face value. It's become clear since then that she's aware of this, but it's not, the feeling is not reciprocal. And she comes here and Siegel is quite dismayed. Siegel, for a lot of things, seems to have things are black and white, and stops promoting her work, basically is very upset with her. And then never really, until the end of his life, never really changes. So this could be a story of like, wow, that was a really difficult situation with her advisor, what might have been. But Braun actually goes on and has still makes a lot of there were still other people supporting her besides Siegel. I want to make a few remarks about these things. So first of all, oh, and I should note, one thing I learned, because I did not have experience with archives before coming here, was you can get a really skewed picture by looking at one archive if you're only looking at one or a small number of people's voices. And you think, I just take everything at face value. And this, even then, there's not much written about Braun. There's really only, I think, one paper where she's a subjective as opposed to some like side figure. And even things where you learn, and there's one paper about her, and it turned out it had some conclusions that also turned out to be wrong, just because I think the author did not have access maybe to this 30 years ago when they were writing the same to all of the documents. So you get a lot of, if you take things at face value, you come up with one story which can be totally flipped. Like I would have had no idea about this, what happened with this, or what was going on with this fiance thing had I just stopped with what was happening here. And I should also notice that for reasons I don't know, maybe it's a thing at the time, Siegel's love life seems to be independently of Braun, a topic predating her coming here, which I don't know what's up with that, but it is a thing that a number of famous mathematicians like to muse on. So, and there were definitely other, in spite of his one true love, there were definitely others at least known to corrupt. So
one true love was not unique.
Yeah, I think in the moment it felt that way, but yeah, it was not unique. This is an early instance of automorphic forms on unitary groups, the thing I was preparing lectures on that led to my going down this rabbit hole, although at first it wasn't much of a rabbit hole until I came here. On unitary groups, and these turn out to be, as I mentioned at the beginning, really important. And one of the reasons is that the symmetric space over which they lie has really nice properties. So these things play an important role for a variety of reasons. But one reason, because of yeah. So this space here, this Hermitian upper half space, that guy. These end up being, if you take quotients of this by appropriate subgroups, end up being the complex points of certain Shimura varieties. And these Shimura varieties parameterize abelian varieties. They're moduli spaces for abelian varieties of polarization, endomorphism, and level structure. And so there's lots of, this is not stuff that Braun was doing. But today, from a modern perspective, would be a reason that a number of theorists would say this is a really good space in which to work. Now, there's lots of groups out there. They're not all this group. But this group ends up like somehow being overly powerful because sometimes, even when you're not working with this group, you can still relate back to this guy. So just to give you, I'm just going to give you quickly 3 examples of where these come into play. So I mentioned I thought the Langland's program would have been the first place I saw them because in my mind, that's where the role is outsized. So in work of Schulze and Anna Cariani, they're looking at Galois, so they use Shimura varieties for specifically these guys. So for U and N, because of the nice properties of the symmetric space, but to study Galois representations in the setting of other groups. So for instance, another natural group you might look at is GLN. GLN symmetric spaces are not as nice. We don't have Shimura varieties, but it turns out that in addition to be able to prove lots of things about unitary groups, but one of the big things they did several years ago was realize symmetric spaces for these guys in the boundary of certain compactifications of these guys. So this is useful, like just if you just want to do unitary groups, but you can push things up further, which is good because not all groups are so nice. So in my own work, can explain properties of Fourier coefficients of Eisenstein series on U and N. This is a thing I have done a lot, and I was surprised to realize that it would have been helpful if I'd known about Hel Braun's work a long time ago. These guys, for instance, you can use to prove, to establish algebraic and p-adic aspects of certain L functions, in particular in the setting of unitary groups. But even when they're of other signatures, you still have to start with this group. So after my thesis, which was of this group, I wrote 2 papers on certain families of Eisenstein series establishing p-adic properties. They're also on this group. And then in work of myself and Michael Harris and Jianshu Li, we construct p-adic L functions for all unitary groups, but it still employs stuff from this particular group. So these are really important. It's not like she just hit some edge case. Likewise, in for studying certain differential operators that show up in the context of certain Galois representations. Again, these groups come into play. This shows up in work of myself and Elena Montalban. When we were working, I realized I needed some result. It would have been nice to have some results that turned out wasn't in the literature, and so I gave it to a PhD student. And along the way, he had to like work something out. It was kind of clunky, but he got it good enough. His paper was published in December. In January, I was looking at Hel Braun's work, and I realized the paper of Hel Braun has never been cited according to MathSciNet, which would have done much nicer, this little like lemma that he needed. So his paper is fine, just if he moves on or I use that, I would probably want to incorporate Hel Braun's work. So in the last few minutes, I want to tell you about this move to algebra. Well, it was a 3A and 3B, so I said there's going to be some geometry and
Can I ask a question?
yeah.
You gave here 3 later applications, but why did Braun develop these? I think.
Oh, so she was initially she's curious about questions. So Siegel's looking at these RQ of T's.
Yeah.
So she's asking analogous questions, but about Hermitian forms, or about Hermitian forms, or not modular forms, just Hermitian forms. And what can I say in those settings? So for example, before this Hermitian form stuff, he has a formula about weighted averages of guys that are in the same GMS, so some equivalence classes. And she's like, what can I do for Hermitian forms? And she does that in her habilitation thesis. So she's interested in analogous questions, but how far can I push this? So that's what leads her in, which I had no idea about. Like when I think about context, like this was not, I was like, well, I told you guys at the beginning, my story about why unitary groups are important, which had nothing to do with any sort of classical. I would have been like, well, if you want to study a Galois representation, automorphic forms turn out to be useful. And you look at these sections, this line bundle and some cohomology and some symmetric spaces and all these modern things would have been my answer. And if I had to like make that up, I could probably say it confidently and probably in front of most number theory seminars, and probably most people would be like, yeah, that sounds right. So, but yeah, that's not all, that's what her motivation was.
But in the end, did she apply these techniques back to like Jacobi?
Yeah. So she goes on and gives analogs of his stuff. But she also, so she does that, and then it leads in the direction I'm gonna get to. But if I only have a few minutes, I'd rather answer your questions, because this is like, to me, the most exciting part, because it's what I use. So if you have another question, okay, I'm glad you're asking that, because that's like the most exciting and interesting thing today. Okay, so the third part is this algebra, which really starts with geometry, which is actually pretty forward thinking. But a thing that happened in between when Siegel defined Siegel modular forms and Hel Braun's involved in that in Eisenstein series, and when she develops Hermitian modular forms, is Siegel has also introduced symplectic geometry. So like the field as a whole is also kind of shifting toward, let's look at these symmetric spaces. What can we say geometrically? And so in these letters with the mathematician Hans Moss. Sometimes it is friendly things like, how are you? Are you feeling better? But sometimes there's math. And she's like, well, what if you're this? And what if that? And but what if the symmetric space this? And so on. And she has this student, Max, either officially or unofficially, Max Kircher. And this is protege, Max Kircher, who's also thinking about these things. And so Braun plus Kircher, they're trying to find a way to handle Hermitian symmetric spaces. So that includes the Siegel upper half space. It includes Siegel upper half space, Hermitian upper half space, and more things in a uniform way. And this leads them to Jordan algebras. These guys are certain. These are certain non-associative algebras. And so the last part of her career is really focused on these Jordan algebras. And this is where I said, if you didn't have the context of what she got there, it just looks like she kind of went back to Germany because she spent only 1 year in the US, then she goes back to Germany. And she's still, when she goes back, at first she's continuing to develop Hermitian modular forms well into the 50s. That's where I found this paper that I realized would have been useful to my student. But then in this natural way, leads her over to this setting and she begins to develop Jordan algebras. She writes to Moss that she and Kircher have really crossed over. They decide algebra is really where it's at. I'm to paraphrase a paragraph that she wrote. So they're really on this algebraic side, even though she was doing analytic things initially, which I think is incredibly forward thinking because that, or maybe it's not forward thinking, but consistent with the direction the field is moving at that time. So I want to just well, I'm going to tell you a story anyway for a minute. So the first day when I went to those archives, for people who maybe have not been to an archives before, which is the case for me before that point, you get these folders and it usually goes from most recent to less recent. And the stuff here concerns Hel Braun's relationship with IAS. And near the top, close to the top, there's an application. So in 1963, she applied to come here again. Apparently it didn't work out. And in that application, she tells us a little bit about what she wants to do here. And she says, and I don't really know, at this time, I know almost nothing about Hel Braun. I'm just like, yeah, she was this person who did these Hermitian modular forms. And apparently now I know she's connected to IAS. And she says, that she and Max Kircher are studying the connections between Jordan algebras and automorphic forms, a generalization of modular forms, and that if she came here, she feels she could make even better progress, especially if she talked and she named some people, one of whom was Otto Selberg, another member here. And this to me was really intriguing and startling because I've been working through this paper she's a pet about certain Rankin-Selberg integrals one of the appendices in this papers had mentioned a mysterious, that literally is the word, mysterious connection, expected connection between these Rankin-Selberg integrals and Jordan algebras, which when I had read that up to that point, I was like, okay, so there's a mysterious connection between something I care about and something I know absolutely nothing about. So not something worth, not a direction I'm probably going at this moment. And to see that there was fascinating to me. There's no evidence that Selberg ever, as far as I can tell, some of you might know otherwise, went down that path. Although you have some things in that direction, at least your work is, Pierre Deline's work is quoted in that appendix. So, so she doesn't get to come here, but she continues to work on Jordan algebras. She and Max Kircher write a book, the first book on Jordan algebras. So I'm now energized by this trip to the archives. I'm like, oh, there's a lot more to see. I start to get her writings, her books. I go to the library here and I get the book out. And, we still have the old card catalog system here. And it was a fascinating who's who. So Bailey, the book comes out in '66. And right away, Walter Bailey of the Bailey-Burrell compactification, for those of you in number theory, has checked it out. He's an NSF postdoc here at the time. Then right after that same year, 66, Helgeson, another major figure in symmetric spaces, checks out this book, and it just goes on like that. It's then got Satake, and so on. All these names who, if you're in this field, like done lots of things, you don't even know, but the things that you, at least I think for my generation, we don't necessarily know where it came from, we just use without second thoughts, but all checking out. Unfortunately, Braun is not very heavily cited, and so it's not surprising that one wouldn't hear of her or know to look for anything or even think to ask what was Hel Braun thinking. I'm still going through lots of stuff. I'm excited to see where it goes. And if you guys have questions or comments, I'm always happy to talk either after my talk or later. And before I stop, I'll note that after questions, if people want to stick around for a few minutes, I have like 5 slides that I think are interesting, but I don't want to use talk time up, but I'll stick around for those in case people want to see those after questions.
Are there any questions?
Yeah.
What an algebra is it? Because she was mainly interested in tube domains.
Yes, she was interested in tube domains, and she was interested in particular, like, she's like, well, we looked at H3 of, or we're looking at Siegel upper half space, where you've got sim for R, and which is really Hermatian for R, but would have looked weird if I started from there. And then you've got the Hermatian space, and then you could look, so then she's like, okay, well, if I'm looking at like Hermitian matrices or something, tensor C, or she's interested in tube domains, so she's like, I could put R here, or I could put C here, if this is Hermitian. Or then she's like, wait, I can put the quaternions here, or I can put octonions here, so she's getting new exceptional groups, and then the structure, well, as you know, things get more difficult. So that's what leads to that. But it's not, I don't think she explicitly, it's possible I just haven't looked at it because I'm a very slow translator. And there's not just the English to German, but the handwriting to recognizable words, part of that. I don't think she ever uses the word exceptional group, but that's certainly somewhere in there for her and character. But yeah, she's looking at tube
The
domains.
classification of a symmetric space we could use from a declared dance.
That's possible. I don't know. Yeah, she must have known that because she wrote a book. So in the book that she, yes, the book has a chapter with that. Yes.
And for an algebra, does we look at arithmetic for them to keep what happens at 2 is especially subtle.
I don't know, but actually, yes, I think so. I don't know the answer, but I think the answer is yes, because I am not an expert on Jordan algebras, but she goes from this situation, then she starts to look at positive characteristic in these letters, and she's like, now I'm looking at p greater than 0, and then there is a paper later where I think she is addressing this, but I'm not 100 at this point. I don't know the answer. I think the answer is yes, but I don't know. It's in the queue of things that are like figure out what's going on here. But I know she does go over to positive characteristic. I'm not sure where 2 falls in the on the boundary of what she understands and doesn't.
Okay, if there are no more questions, let's thank Ellen again.